In this video, we're going to go over some of the basics of aromaticity. We'll look at some different molecules and classify them as aromatic and try to see where some of the special stabilization in aromatic systems comes from. Just to look at some of the basics of aromaticity, keep in mind that the aromatic moiety is especially stable and quite unreactive. So for example, if we look at benzene, which is sort of the quintessential aromatic compound, it's an aromatic hydrocarbon that doesn't react with reagents that will typically react with regular alkenes. For example, if you use HBr and react that with an alkene, you're going to add H and Br across the double bond. Or if you use Br2 and react that with an alkene, it's going to add bromine across the double bond. Okay, in comparison, even though benzene has these three double bonds present, if you add HBr or bromine to benzene, no reaction occurs. And the reason for this is because benzene is much more stable than a standard triene containing three bonds. This can also be observed if we think about the heats of hydrogenation. For example, if we take a single alkene and we add hydrogen and palladium catalyst to that, we can hydrogenate this double bond and add H2 across it. This reaction is exothermic, and the delta H for the reaction is negative 28.6 kilocalories per mole. So if this is the energy released from hydrogenation of one double bond, then we would expect, if we're hydrogenating three double bonds, well, this number should just be tripled. So if we triple this number, the expected heat of hydrogenation would be negative 85.8 kilocalories per mole. But experimentally, it's been found that upon hydrogenation, only negative 49.8 kilocalories per mole of energy is released. So that means that benzene is lower in energy than expected, and that lower energy is a result of a special stabilization. And we call this aromatic stabilization. And if the actual energy is negative 49.8, the expected is negative 85.8, subtracting that out, there's 36 kilocalories per mole of energy sort of unaccounted for. And that is the aromatic stabilization. And that is the aromatic stabilization energy. Now let's take a look at the criteria or requirements for aromaticity. In order for a molecule to be aromatic, first, it must be cyclic. Second, it must be completely conjugated, meaning every atom in the cycle must contain a p orbital, so it's a continuous system of p orbitals. It must be planar, and that allows for the parallel alignment of these p orbitals. And it must follow Huckel's rule, which is a 4n+2 rule. And if we count up the pi electrons, they need to equal 4n+2, where n is an integer, 0, 1, 2, 3, etc. If all four of these criteria are fulfilled, the molecule is aromatic. If any of the first three criteria is broken, then the molecule is just classified as non-aromatic. And if criteria 1 through 3 are fulfilled, but the pi electron count instead equals 4n pi electrons instead of 4n+2, where N is 0, 1, 2, 3, etc., then we classify the molecule as anti-aromatic. Anti-aromatic compounds are especially unstable and are actually pretty rare. First, we'll take a look at benzene and classify the criteria for aromaticity. We all know that benzene's an aromatic molecule, but let's prove it with our criteria. First thing, it's a cyclic ring. Second thing we want to see, is it completely conjugated? Well, every carbon that has a double bond contains a p orbital. So if we put a p orbital on every one of these carbons, we see that every carbon in the ring has a p orbital. It is completely conjugated. Okay, the next thing, is it planar? Well, every one of these carbons on the ring is sp2 hybridized, so this is going to have a planar orientation. Okay, finally we just have to check Huckel's rule, and that's the 4n plus 2 pi electron rule. Well, every double bond is 2 pi electrons. So here we have 2, 2, and 2. So we have 6 pi electrons. So now let's do 4n plus 2 equals 6. Solve for n equals 1, and that works. So benzene, of course, is aromatic. Now let's look at cyclobutadiene. Cyclobutadiene, like benzene, it's cyclic. Every carbon contains a p orbital, so it's completely conjugated. It's going to be planar. For our pi electron count, we have 2 double bonds, each contributes 2 pi electrons, so there's 4 pi electrons. Well, let's try Huckel's rule. Set 4n plus 2 equal to 4. Then we get 4n equals 2, n equals 2/4, or 1/2. Well, that doesn't work. But we can try the anti-aromatic equation, and we'll set 4n equal to 4, which is our pi electron count. Now, n equals 1, that works. So our first 3 criteria are fulfilled, and then our fourth criteria fulfills the anti-aromatic equation. So cyclobutadiene is anti-aromatic, and it is a very unstable molecule. Next, let's look at cyclooctatetraene. And before we get into this, there's one caveat that I want to make you aware of, and that has to do with rings that contain 7 or more atoms. They have enough flexibility to bend out of planarity, and they'll do that to keep from being anti-aromatic, which will then just make the molecule non-aromatic. Now typically, larger rings, if all the criteria is fulfilled to make them aromatic, they'll stay planar and be aromatic. But if they're looking like they're going to be anti-aromatic, rather than gaining that anti-aromatic destabilization, if they have 7 or more atoms, they'll just bend out of planarity, so they don't have to be. So let's look at cyclooctatetraene. Okay, so first, it's cyclic. Second, every carbon is part of a double bond. It's completely conjugated. Next, let's look at our pi electron count. 2, 4, 6, 8. So we have 8 pi electrons. Well, if you plug that into Huckel's equation, it's not going to work. So if we do the 4n equation, set that equal to 8, n equals 2, it fulfills all the criteria to be anti-aromatic on the first look. But this particular ring has 8 atoms, and what it's going to do, instead of becoming anti-aromatic, it's just going to bend and not be planar. Since it's not planar, that criteria is not fulfilled, and rather than being anti-aromatic, this molecule is simply non-aromatic. Now let's take a look at some ions that we might have to deal with. First, we'll look at a carbocation. And anytime you have a carbon bearing a positive charge, that positive charge, you can sort of think of it as residing in a p-orbital on the carbon. So if we draw this cyclopropenyl cation just a little differently here, so we can give it a little more three-dimensionality. Okay, here are the p orbitals from the double bond. And then here's the p orbital where the carbocation is at. So this carbocation gives us a p orbital in that carbon. So we can see that, of course, the molecule is cyclic. It's also completely conjugated. Okay, so next thing, we just have these 3 atoms. All the carbons are sp2. It's planar. Okay, so now we need to get our pi electron count. Well, these 2 electrons in the double bond count. The carbocation is sort of a void of electrons, so we don't count anything there. So all we have here are 2 pi electrons. Well, let's try Huckel's rule. 4n plus 2 equals 2. 4n equals 0. N equals 0. And that's just fine. So this fulfills all the criteria for being aromatic. And this is an especially stable cation because it's aromatic. Now let's look at a couple of carbon anions. Okay, and the thing to keep in mind here is that the carbon anion is typically representing a lone pair on the carbon. Okay, and this lone pair, it will be in the p orbital if it makes the molecule aromatic. If putting that lone pair in the p orbital makes the molecule anti-aromatic, it's going to stay out of that p orbital and just stay in a regular hybrid orbital. So let's look first at the 5-membered ring. The molecule is cyclic. If we put, and let's just first assume that we put this lone pair in a p orbital, and of course we'll have a p orbital where all the double bonds are. So if we do that, it is completely conjugated. Okay, it's going to be planar. And then for our pi electron count, we have 2 in this double bond, 2 in this double bond, and we count the lone pair since we put it in a p orbital. So we have a total of 6 pi electrons. Well, let's try Huckel's rule. 4n plus 2 equals 6. N equals 1. That works, and this particular molecule is therefore aromatic. And that lone pair is in the p orbital. Now let's take a look at the 7-membered ring. With cyclic, if we put the lone pair in a p orbital, it's completely conjugated. And then if we do that, we have 2, 4, 6, 8 pi electrons. Well, 8 pi electrons will not satisfy Huckel's rule. It will actually satisfy the rule for anti-aromaticity. So this is starting to look like an anti-aromatic compound. Okay, but there's two ways to look at this. One, this particular molecule contains 7 atoms. It can bend out of planarity to keep it from being anti-aromatic. So that would just make it non-aromatic. The other way you can think about this is maybe just don't put the lone pair in a p orbital. So instead, if we don't put this lone pair in the p orbital, we have 4 things around the carbon, and this lone pair can just reside in an sp3 hybrid orbital. If it's not in a p orbital, it's not completely conjugated, and therefore non-aromatic. So again, only put that lone pair in the p orbital if it makes it aromatic. Finally, we're going to take a look at a few heterocycles that you might run into. First, we'll look at pyridine, and the hardest part about these is knowing how to deal with any lone pairs on the heteroatom. So basically, you're not going to count things twice. So for this particular one, we have these 2 pi bonds in the ring. The third pi bond is on the nitrogen. So it already has a p orbital because of the pi bond. Therefore, we don't need to count this lone pair in a p orbital because the nitrogen already has the p orbital and the molecule is completely conjugated. Of course, it's cyclic. Okay, now if you look at the hybridization of this nitrogen, we have 3 things around it, 2 bonds and a lone pair. It's sp2. And this lone pair must just reside in an sp2 orbital because the p orbital is used up with the pi bond. For your pi electron count, we count these 3 double bonds, 6 pi electrons. You can set that equal to 4n plus 2. N equals 1. So pyridine, of course, is aromatic. Next, let's take a look at pyrrole. So again, we have a nitrogen with a lone pair, but now there's not a double bond on that nitrogen. So it doesn't already have a p orbital from the double bond. So what we need to do is try putting this lone pair in a p orbital. Then each of these double bond carbons contain a p orbital, and if we have that lone pair in the p orbital, it is completely conjugated. Of course, it's cyclic. For our pi electron count, we count the 2 double bonds. We also count this lone pair that's in the p orbital, so 2, 4, 6 pi electrons. Set that equal to 4n plus 2, n equals 1, and this molecule will be aromatic. And it's aromatic because this lone pair can go into a p orbital, giving us a conjugated system. The last one we're going to look at here is furan. And it's very similar to pyrrole, where we have a heteroatom with a lone pair. The only difference is oxygen has 2 lone pairs. Well, when thinking about aromaticity, we're only going to put one of these lone pairs in a p orbital. Then we have the double bond p orbital, so it's completely conjugated. It's cyclic, it's planar. For your pi electron count, count your double bonds, count the one lone pair that you put into the p orbital. We have 6 pi electrons, and that does satisfy Huckel's rule. So therefore, it's aromatic.